Okay, so it is time to start our session. Welcome to all of you who have joined us to the session entitled Application of Methods in Design Practice 1. There will be a follow-on session after the keynote, Design Practice 2. My name is Oscar Nespoli from the University of Waterloo. We have a great lineup of talks. I'm excited because they all involve quite a variety of artifacts that feature design practice and some innovative designs and processes of designing. So the format will be, I will introduce the speaker, and then Ivan, who's helping me, will play the video, and then I will introduce the next speaker. Please use the chat feature. Be sure that you select the session tab at the top right as opposed to the event tab, so that your chat will actually show up in the session to all the participants. And please direct your question to one of the speakers, a question for example, Manfred. And please don't be shy to ask a question. Okay, I think that's all the logistics. Without further ado, let's get started. I'd like to introduce our first speaker, Dr. Manfred Grafinger from Vienna. Has been working in virtual product development at the Technical University of Vienna since 2011. He's working in the Institute of Engineering Design and Product Development, mainly in the fields of computer-aided engineering methods. So without further ado, let's hear about his paper entitled Using Kinematic Analysis to Develop a New Tooth System for Gearings with Variable Shaft Angle.
Welcome to my presentation, Using Kinematic Analysis to Develop a New Tooth System for Gearings with Variable Shaft Angle. My name is Manfred Grafinger from TU Wien, Department for Virtual Product Development. First, I want to give you a short overview of the content. After an introduction into the use case, I want to describe why standard gears for variable axis angle cannot be used. Then I will follow up with the kinematic gear model and the parameter study on coned crown gears, followed by the optimization with spherical shaped crown gears and the description of validation on a prototype. At last, I will close up with a short summary. For the development of an omnidirectional treadmill, a tooth system is needed that can transfer continuous rotation while variable angle of rotation axis occurs to ensure that the revolving belt units thread incorrectly into the driving gear shaft. The necessary span of angles is from 0 degree to 60 degree. The old crown gear system can be redesigned for different axis angle, but it is not applicable for variable shaft angle. Load recommends the TYRES gearing for variable shaft angle application. A big drawback of TYRES gear is the required space for the teeth on the outer cylinder barrel. In the application of the treadmill, the driving involute gear is seated at this location. Therefore, TYRES gear is not applicable, and a new tooth design is needed. For this reason, a parametric kinematic gear model was built to investigate the possibility of a coned tooth gear system. Axis angle and cone angle were defined as parameters whereby cone angles from 9 degree to 25 degree were investigated, and for each of them the axis angle was varied from 0 degree to 60 degree. A swept volume was created to check the kinematic for tooth collision during motion. It came out that no configuration without collision of the cones while rolling over the teeth can be found. The table shows the penetration at different combinations of cone angle and axis angle. It can be seen that smaller cone angle works with larger axis angle and vice versa, but there is no possible cone angle for all required axis angles. To eliminate the collisions and head relief can be promissory. The driving gear will be made with FDM 3D printing, while the other gear will be manufactured of aluminium. For the ease of milling, the aluminium wheel keeps the constant cone angle, and the 3D printed wheel gets the spherical tooth relief. The new tooth form now consists of a circular arc with 3 tangents, as you can see in the right picture. The parameter for cone angle on milled wheel and tangent angle at pitch circle on printed wheel is set to 90 degrees, because at larger angles, the gaps between tooth feet get too small for milling cutter. Parameter variation of foot angle and head angle was investigated with the result that about ±2 degree angle deviation is necessary to avoid collisions. With this parameter set of 7 degree, 9 degree and 11 degree from foot to head, the final shape was specified. To validate the new developed tooth system, a test bench was built. The 3D printed wheel is driven over a standard involute gear that later also should be applied in the treadmill. The movable part is connected with a pivot joint and is swiveled by a spindle drive to variate the axis angle during rotation. The test bench was operated over 500 hours without any identifiable wear at the tooth flanks, so it could be illustrated that the tooth profile works without any collision over the full range of axis angle. To sum up, neither standard crown gears nor torus gears are usable for this application. The parametric study shows collision for cone teeth. This could be solved by spherical teeth with ±2 degree tangent deviation at head and foot. The working parameter set at the end was 9 degree cone angle at driving wheel with 7, 9 and 11 degree cone angle at driving wheel. This could also be validated by a test bench. Thank you for your attention.
Excellent. Thanks so much for that, Manfred. I'm looking forward to asking some questions at the end of the presentations. Okay, so yes, thank you very much. Okay, our next paper and presentation is being presented by Daniel Miller. I don't know if I pronounced that correctly. Please correct me, Daniel, if it's wrong. And his paper, his contribution is entitled Optimization of Welded Beams, How Cost Functions Affect the Results. And so we will hear your video now.
Hello, my name is Daniel Miller, and my presentation is concerned with the influences of cost functions on the results of the welded beam optimization. In other words, we wanted to assess whether the selection of objective functions will have a significant influence on the outcomes. So, in the modern time, it is expected that the product will fully perform its primary function. Thus, by implementing additional beneficial properties, we are able to make our product more attractive on the market, mostly through the optimization process. However, in order to carry out the optimization process, we have to create a mathematical model. And the mathematical models are generally built using existing knowledge. So if we are developing a new product, which is complex, the modeling process will be rather complex too. One of the first steps in model creation is including the boundary conditions, which are most often based on the available technical literature, mostly standards and handbooks. On the other hand, the objective functions are a bit harder to. There is often no consensus between the researchers, so there will be several different formulations available for the same aim. When considering the beam design, it is mostly important to decrease the weight and associated costs. The weight and volume are easy to define, and there is no room for discussion, while beam cost is a bit harder to determine. So we wanted to solve the following research question, and which is how do different cost calculation methods affect the optimization of mechanical structures? We have used the beams as an example. So regarding the beam manufacturing, the process has several phases, and most of the formulations include the cutting phase, then the surface preparation, which is necessary before welding, then we weld the plates, then we have to manipulate them into the position, and lastly we have a painting and coatings. That is a simplified process. To carry out the study, we have used a beam with a simple cross section as shown on the left side. On the right side we can see the research process. The important part is that the research process is completed with 3 different cost calculation methods. So first we have created 3 situations. We have had 3 beams with different loads. Here we can see all 3 cases, and each case was then optimized using 2 objective functions. Beam volume, which was same for all the cases, and production cost, which included both the manufacturing and the materials. 3 different cost calculation methods were used, so we can say that for each of the 3 cases, the optimization process was repeated 3 times. Formula are shown here, and more details can be found in the paper. Now, the results were rather interesting. So, for the first case, the 12-meter beam under a 10 kilonewton load, we see that all 3 objective functions have given identical results. So, regardless of the objective function for cost calculation, the result will be the same. And in the second situation, we have a bit different results. So there is no consensus similar to the previous case on the first segment of the Pareto optimal line. While when considering the plate thicknesses, they are the same for all the 3 cost calculation methods. In the last, in the third case, we also see that the results are identical for all the 3 methods. Also, in addition to Pareto fronts, we wanted to show 2 additional findings. So first, the abrupt changes were mostly caused by changes in cross-section classes. So the cross-section classes were defined by Eurocode, and also the lateral torsional buckling was an active boundary for all these specimens. It is much more significant and limiting than bending moment. And finally, the conclusions. We have concluded that the variations which are caused by using different cost calculation methods were not significant, so we recommend using the simplest one. And also the absolute costs that are given by each of the methods were not crucial for the optimization, as only relative values and differences between different designs were needed in order to obtain optimal results. So that will be all, and thank you for your attention.
Okay, excellent. Thank you, Daniel. And I neglected to introduce Daniel. He's currently working as a postdoctoral researcher at the University of Zagreb, and his main area of interest is in the optimization of mechanisms, primarily gears and powertrains. And he mentions he also likes dislikes grading examinations, like most of us do as well. Okay, that's excellent. I have a couple of questions for you too at the end of this. On to our third paper of the session. So we're moving from welded beams now to all-terrain vehicle tires in agriculture. And before I introduce the presenters, I want to say that this has received an award for one of the top 10% papers as rated by the reviewers. So congratulations to you. The paper is going to be presented by Dr. Shayne Gooch and also by Tim Petterson, who join us from Christchurch, New Zealand at 1 a.m. in the morning. So thank you so much for making that effort to join us. Dr. Gooch is the Dean of Engineering, academic at the University of Canterbury, and the director of Hales and Gooch Limited, both located in Christchurch, New Zealand and Chicago, USA. And his research interests include engineering design, design for people with tetraplegia, and design of flexible vibrating structures. Looking forward to your video presentation. So go ahead, Ivan.
Good afternoon. This presentation examines and quantifies various factors which affect the rolling resistance of ATV tyres in the New Zealand dairy farm environment. The study came about as part of a larger project based on developing an electric vehicle to perform tasks autonomously on a typical New Zealand dairy farm. The project was focused on developing a commercially viable EV, which relates to producing an EV with a similar range and vehicle cost when compared to an internal combustion equivalent. The expensive nature of lightweight batteries makes this task exceedingly difficult, and therefore the range had to be maximised by minimising the forces opposing the vehicle's motion. Of the 4 main opposing forces, rolling resistance is the only force constantly present throughout the vehicle's motion. It results in significant energy losses due to the deformation of the tyre and terrain. However, due to the complex nature of tyre-ground interaction, rolling resistance for small off-road tyres has been difficult to quantify, with very limited amount of data and research available for these tyres. The rolling resistance also had to be defined to optimise the size of the powertrain components. The factors affecting rolling resistance can be broken down into three main categories: tyre, operational, and environmental conditions. Tyre factors include the construction, type and quantity of rubber used, tread design and depth, as well as tyre size. Operating conditions include the normal load, inflation pressure, and vehicle velocity, while environmental conditions largely relate to ground firmness and surface roughness. To examine the effects of these various factors, I designed and fabricated this test rig at the university workshop. The test rig consists of a simple A-frame that was towed behind a vehicle, which allowed the tyres, normal load, and inflation pressure to be easily changed in the field. A 200 kg load cell was placed between the front of the frame and the trailer coupling. Two vertical pipes located the gym weights directly above the wheel axle. The force from the load cell was measured in parallel with the test rig's velocity. As shown here, the test rig was towed around a path set up on a dairy farm in Canterbury, New Zealand. It consisted of short grass, long grass, and a hard-packed laneway, with measurements recorded at both 10 and 20 km per hour. 7 different pairs of ATV tyres were tested, with the normal load being adjusted by adding gym weights to the test rig. 5 normal loads were tested, ranging from approximately 20 to 230 kilos on each pair of tyres. All tyres were operated at 5 psi except for tyre 2, whose inflation pressure was adjusted from 2 psi to 11 psi. All 7 tyres produced similar linear patterns as displayed here. As the normal load increased, the rolling resistance also increased at a proportional rate, verifying that the rolling resistance is proportional to the normal load for these ATV tyres. Due to this relationship, the results can be presented in terms of rolling resistance coefficient, where the coefficient represents the operational, environmental, and tyre factors. This graph compares the rolling resistance of the 7 tyres to each other. It can be seen that as the tyre diameter increases from tyre 1 to 4, the rolling resistance coefficient decreases by approximately 50%, which agrees with previous research. These 4 tyres have similar properties other than their change in diameter. Tyre 5 has a similar rolling resistance to tyre 4, however tyres 6 and 7 have much higher values. Tyre 6 is significantly wider than the other tyres. This factor, combined with its bias ply construction, is responsible for its higher rolling resistance. The extra width, bias ply construction, and small rim means that the cord lengths are very long, which produces a greater wiping motion and a larger hysteresis cycle. The firm soil conditions meant that no noticeable sinkage occurred, negating the flotation benefit of wider tyres. Tyre 7 also produced high rolling resistance values, despite it having the largest diameter of the tyres tested. The reason for this high value is both the tread pattern and tread depth. The tread depth was more than double that in the majority of the other tyres, which was coupled with a wide, aggressive tread pattern producing a rough rolling motion. This study provided vital information pertinent to the EV's powertrain design. Without the study, the motor power and torque requirements would not have been accurately determined. The study also provided significant insight into the influence and magnitude of ATV tyre properties on rolling resistance. This was crucial in reducing the developed EV's rolling resistance and hence increasing its overall efficiency and range. The results of the study were a major factor in making the developed EV more competitive and commercially viable when compared to an ICE equivalent, and produced a significant range improvement when compared to other commercial off-road EVs.
Okay, excellent. Thanks for that presentation, Shayne. A very relevant topic for today's automotive developments. Okay, on to our 4th paper for the session. It's entitled Design Modification of an Innovative Split Single Two-Stroke Engine, and it will be presented by Aljoscha Zahn of the University of Bayreuth in Germany. Aljoscha completed his Master's of Science degree in Automotive and Mechatronics from the University of Bayreuth, and since then he's been working with the Chair of Engineering Design and CAD at the same university, and his role is scientific assistant. And so we look forward to listening to your presentation, Aljoscha.
Good afternoon, ladies and gentlemen. In the following session, I'd like to give you a brief insight in the current development stage of our split-single two-stroke engine. I will first discuss the reason that motivated us to build this prototype. Afterwards, we will have a look on our current design objective and the steps leading to it. The development of modern combustion engines is subject to various driving factors. The highest demands are placed above all on the reduction of pollutant emissions and fuel consumption. Considering the electrified mobility in the future, combustion engines can still make a major contribution as mobile power generators or range extenders. Two-stroke engines offer enormous advantages in terms of their simple design, weight and space savings, and high performance. A two-stroke engine in which the high fuel consumption caused by scavenging and the resulting carbon-hydrogen emissions are minimized is essential for a successful establishment on the market. An interesting concept to reach this goal is the split-single engine after a patent of Arnold Zoller. We were able to apply this concept in a prototype build operating with natural gas. During the development of the prototype, practical aspects such as strength and durability were prioritized. The current objective is to prepare the concept for mobile applications. Therefore, the next step is to increase the power-to-weight ratio of the engine through a new lightweight design of the housing components. Previously, the component cylinder head and cylinder block have been revised since they were vital for improving the scavenging process and the cooling of the liners. The crankcase, which is currently designed as a welded steel construction, still offers an enormous potential for further weight reduction. The crankcase serves the accommodation and support of the crank drive and has to absorb the forces and torques during operation. Thus, an important aspect for the overall design of the crankcase is the dimensioning of the bolted joints, especially in the area of the bearing seats. Here we use the guideline given by VDI 2230 called Systematic Calculation of Highly Stressed Bolted Joints. The guideline lays down the process for the analytical analysis. Furthermore, it includes strategies for modeling bolted joints and finite element analysis in form of 4 basic model classes. The first model class neglects the geometry of the bolt but allows for a calculation of the cutting loads in the contact interface. These loads can then be used for the dimensioning of the bolted joint via the analytical approach. In the following classes, the geometry of the bolt can be represented in a FEM model, which allows for further investigation of the contact state of the interface. We used the model class 3, which includes the bolt as a volume body and further allows to consider the pre-tension forces. For the redesign process, we derived an iterative process chain using computer-aided X tools. The redesign is based on their operating experience on the testbed for the current prototype. A CAD system is initially used to create the new crankcase design, which maintains compatibility to the remaining engine parts. In the next step, a simplified FEM model is used to calculate the cutting loads for the individual bolted joints. For the dimensioning process, a design software for machine elements is applied, which provides the previously discussed guideline. Afterwards, a new FEM model is prepared for verification of the design. Here, undersized or unfavorably positioned bolted joints can easily be identified. If the new design meets the requirements regarding stiffness and strength, the model is prepared for manufacturing. Finally, a production simulation using a CAM tool is used to make sure the design is manufacturable. Since the design process depends on iterations between the systems, fallbacks have been defined if the initial design does not meet the requirements and has to be adapted. Alternatively, the selection of a material with better mechanical properties can be considered. Our final prototype of the crankcase was manufactured from an aluminium casting alloy by gravity die casting. With the redesign of the crankcase, a new engine prototype could be completed. In future work, the durability of the new design will be validated in testbed trials. A future topic will also be the investigation and improvement of the NVH properties, which are essential for the mobile application of the engine. Thank you for your attention.
Excellent. Thank you very much, Aljoscha. Your design looks good. You know, I always feel that a design should be functional, but it also should look good. So good job on that. All right. Coming to our last presentation for the session. until we start our discussion. And please, if you have questions, go ahead and put them in the chat so I can curate them and organize them. Don't be shy. Our next presentation is entitled On Prototyping Methods to Leverage Non-Rigid Materials in the Early Stages of Engineering Design. And it is presented by Marius Auflem from Norwegian University of Science and Technology in Norway. And Marius currently works at the Lærdal Medical as an industrial PhD candidate through the Department of Mechanical and Industrial Engineering at the Norwegian University of Science and Technology. And he does research in early stage product development in the context of medical training and simulation equipment. So it's very interesting. Now we'd like to listen to your presentation.
Hello, everyone. My name is Marius Auflem, and I will be giving this brief presentation of our paper titled On Prototyping Methods to Leverage Non-Rigid Materials in the Early Stages of Engineering Design. It has been written by Hans Hagenes, Jørgen Falck, Otto Martin Steinert, and myself. In this research, we are highlighting some of the trade-offs a design engineer should prioritize when prototyping in the early stages of engineering design. More specifically, we are discussing how to leverage non-rigid materials in these stages of development where it is not evident which methods, tools, and materials that is best suited the given design problem. Non-rigid materials have opened for product opportunities, new product development, research, and innovations in fields such as soft robotics, medical technology, and compliant mechanisms, to mention some. Hence, how to explore this range of materials is of interest. In the context of the early design stages, we consider prototyping to be more than just the creation of prototypes. It is a learning activity where designers could iteratively design, build, and test prototypes to bring answer to open design questions. More so, prototyping is an important tool for design teams to communicate ideas, inform decisions, and learn. The reason why we are addressing this is that how to leverage non-rigid materials in the early design stages is not evident. Various methods and materials exist to generate components with flexible attributes, and through projects we have conducted in our lab environment, we have found that prototyping is important for teams to explore this in their product applications. More so, we have seen how different methods of generating such prototypes are affecting the prototyping outcome, both in terms of prototype attributes, but also the activities the design teams are performing. By reviewing 4 different case projects utilizing different approaches to generate non-rigid prototypes, we have described their methods for prototyping by 5 different parameters: speed, modifications, design freedom, fidelity, and resolution. By this, we are attempting to discuss how various methods are not only affecting the tangible outcome of the prototyping, but equally interesting, how it affects the activities carried out within design projects. With the term speed, we are evaluating if a given method accommodates rapid development iterations and hence fast learning. With modifications, we are evaluating if a given method are accommodating design changes as a response to revealed insights. Design freedom evaluates a given method's freedom of choice concerning materials, geometrical, and size constraints. Fidelity is considered the obtainable degree of closeness to an eventual design, while resolution as the obtainable amount of detail given the selected method. The 4 projects and prototype methods we have reviewed are using soft prototyping to conceptualize an articulated airway for medical training, using living hinges to prototype a compliant chest for resuscitation mannequins, fused filament fabrication of a spring component for a drug mixing container, and prototyping using molding for a heart phantom. By subjective evaluation of the methods utilized in these case projects, we have mapped out their strengths and limitations, which can be seen represented in this figure. From our insights, it is possible to give normative recommendations to design teams in early prototyping stages, putting emphasis on the intent and predicted outcome of their design activities. As with other materials, being aware of what one is trying to achieve with their prototype, we discuss that various methods of prototyping are yielding the outcome, and also affecting how fast a team could obtain insights, adapt their prototypes to the revealed insights, or create a sufficient representation of their design idea. This way, the various methods are suited different design challenges and intended use for the prototype. For example, how an internal experiment could be greatly benefited from rapid cycles, whereas an external user test might require a higher degree of resolution and fidelity for the prototype to be evaluated. With the recent attention to the importance of prototyping in engineering design, we hope that our research could bring some insights on prototyping activities and how choosing different methods could help leverage non-rigid materials given various challenges found in early design. I thank you for your attention and hope that you find this research interesting. Feel free to ask us any questions or contact us at a later instance.
Excellent. Thank you so much for that, Marius. Yes, there's a common paradigm that prototypes should be done after you do the design. And in this case, it's a good strategic move to put it at the very beginning. Okay, so now we're in our discussion portion of the session. We have almost half an hour, so that's a good amount of time to get some discussion going. And I see that two presenters have started off the discussion, which is great. And you can enable your microphones if you wish to ask the questions. So the first one is from Aljoscha to Manfred. Go ahead, Aljoscha.
Yeah, thank you, Oscar. Okay, thank you for presentation, Manfred. I had a question regarding your optimized design for the tooth shape. Yeah. And I wanted to know, how did you optimize the design of the tooth shape? Was it a try and error approach, or could you automate the process?
Thank you for the question. So it couldn't be really automated. What we did is a wide parameter field that we tested. This can be automated, and from this parameter field, we get the results in which parameters maybe we can get the less overlapping of the teeth. But at the end, the decision for the 9-degree cone angle on the first gear was for manufacturing reasons, because in the milling of the teeth we had some tools with 9-degree or 12-degree or 15 degrees in our workshop, and the 15-degree tools, the 12-degree tools were too wide in the feet width. So we hadn't enough space for these tools for the number of the feet we need on the pitch circle. So we decided to use the 9-degree cone circle on the milled wheel, and then the other wheel was try and error to get the best combination of the angles for this.
Okay, thank you.
So it was two-step. The first step was a right parameter research for possible solutions, and the next step was the optimization for the manufacturing. Did it answer your question?
Yes, completely. Okay. Thank you very much.
Okay, now Manfred, it's your turn to ask Aljoscha your question.
No, I have a question back. I wondered about the efficiency. You told us the split cylinder can be more efficient with less fuel consumption than the single cylinder. I wondered a little bit about this, because you have two pistons, you have a lot of more friction in the system. Mm-hmm. How does it come?
The efficiency aspect is regarded towards the pollutant emissions. In a conventional two-stroke engine, you have the problem that your fresh gas can almost immediately leave the combustion chamber through the exhaust outlet port. That heavily depends on the scavenging process you use, but you will always have some hydrogen carbon emissions in a conventional two-stroke engine. The advantage of the split single concept is that the scavenging process is much easier to control. In our case, the piston for the exhaust outlet closes before the fresh fuel air mix can reach it. So though you can minimize the lost hydrogen carbon emissions through this concept.
Mm-hmm. Okay. Yeah, that makes it more clear. Yeah. Thank you.
Okay. Great.
Okay, great. Thanks for those questions. Are there any questions from our participants, other participants? Please type them in the chat. In the meantime, I have a question for Shayne and Tim. I didn't notice in your paper when I read it, did you find an effect of the type of tread on the tire on rolling resistance? Or was that something that you investigated?
We only basically did this the study here. We didn't isolate the property basically straight away, but we did find that significant tread height and wide spacing between the lugs did affect the rolling resistance quite a bit, but further research would need to be done to sort of determine what sort of tread is best. And it's sort of with the ATV tires, it's a balance between minimizing your rolling resistance and also maintaining traction. So it's very much sort of depends on what terrain you're in as to what tire you would choose. Yeah.
Mm-hmm.
Is that
okay?
Is that what you're asking?
Yeah, my understanding. Yeah, no, that's fine. My understanding, I'm not a farmer or knowledge of agriculture, but I did have someone give a presentation on a design that they had that would automatically reduce the pressure in large tractor tires when they went onto a field. And of course, the purpose of that would be to try and preserve the soil from being compacted. I noticed that tire pressures seem to be low. Is that the reason for the lower pressures in the ATV tires?
ATV tires typically operate, in very low. It's just their standard operating pressure. That's what they're designed to operate. It's between sort of 3 to 8 PSI is pretty typical. But yeah, they are designed to operate that low to give you a larger footprint to basically give you more traction as the main reason, more than to reduce compaction. Yeah.
Okay, good. Thank you. Are there any other questions? Any questions from panelist to panelist?
I got a question, maybe towards Shayne again. I wanted to know, were the tires you tested brand new or were they already run in?
They were all mostly used, so they weren't brand new. That was mainly due to accessing tires. I basically borrowed them from friends, so we were sort of limited a little bit with funds. Like we couldn't go out and buy 14 pairs of tires, so we used what we had, but managed to get a variety and a range that sort of suited what we wanted to get out of the study.
Okay. Any other questions? Now, the title of the session is Application of Methods in Practice. And so I'm curious, were there any particular methods you found were effective or not effective in realizing your designs?
When I made to say something about this, what I found out, we started with the optimization with the wide parameter range, and I hoped to find out the parameter setting that will work well, and we find out the best angle of the T should be about 15 degrees, 20 degrees, and then I went with my ideas to the workshop, And then I got back. No, it's not possible to manufacture, and we should do something else. So the optimization process is one thing, but the next thing is what is possible for manufacturing with the tools that are available in the workshop. So maybe this methods alone are not always the only thing.
Yeah, and well, this is a unique feature of design practice, is when you have an expectation for your design and then you implement your design, and of course usually we fall short, and so we learn from that kind of experience. So
yeah,
that's good. Are there any other experiences from other presenters in realizing their designs?
I can give a brief comment on that, because we are in our lab environment, we are conducting several experiments going over and over in terms of a lot of user-centered design challenges, of course, and really early stage product development as a focus. And sort of our approach to this is that if we can reduce the time until we have a testable artifact to evaluate if the design is something to pursue or not, if we can minimize that time, maybe we can maximize the number of potential directions that you can take in your project. So that's more in a product development context, where you want to maybe explore a broader solution space than to figuring out one specific design challenge. And I think that's all about how much uncertainty you are facing at the time. So we see at least the prototyping aspect is incredibly important, at least in our experience.
Mm-hmm. Yeah, I can see that, both in eliciting user requirements, but also in predicting or verifying the behavior of these very flexible and very geometrically complicated shapes too. I see that you had a heart that was made out of a flexible material. Could you expand on that particular project, Marius?
Yeah, that was a really interesting one. We had this project where we had this material that we had been working on for a different reason. It's a silicon compound that is also ultrasound compatible, and we ended up in a discussion with some researcher at the hospital that wants to do. They want to research the flow conditions within the heart, and mainly not on the flow, but on development of new ultrasound equipment to investigate the flows within hearts. And of course, hearts are pretty hard to come by, and especially have complete control over test scenarios and sort of all the external variables. So that project actually became, I think the team developed something between 10 or 20 different hearts that were tested by ultrasound experts down at the hospital facility. So that was really interesting.
So that's interesting. Yeah, very interesting. I had a question also, Marius, regarding your evaluation of the different methods along those 5 scales. You said it was a subjective evaluation. Could you maybe explain what you mean by that?
Yeah, it's of course no standards that we have tried to compare them up against. It's more that we see specific strengths and limitations when we have reviewed the projects more than what they do in the specific activity. So we have tried to identify how long time does it take before they produce a testable prototype, and how does it affect the activity. So it's more of a review, so to say, of how the teams are interacting and what they are doing in the project. This is of course in a university setting in our prototyping lab, but it's still interesting to see that being aware of what methods you decide to use, it heavily impacts both how explorative the team members are, and also how fast they come to conclusions regarding following a path where they haven't thought of design, or if they decide to change direction.
Yeah, that's an interesting sort of new area of investigation, perhaps, right?
Yeah.
That's really good. Yeah, thanks for that contribution. Okay, we have a question from Daniel to Manfred. Go ahead, Daniel.
Oh, thank you. As I've written here, we are about to try a similar thing. We have a problem in which we need the great shaft axis flexibility, and also we need to transmit torque from one shaft to the other. So I'm not sure which bearings to select, and how many bearings will I need, since probably 2 axes will be moving. So I wanted to ask Manfred, how are they solve this problem?
So I think this when I attended your question, the problem is not like similar, because we have no flexible axis. We have the problem. Maybe I can share my screen to show you the picture. Is this possible, Oscar?
Yes, it is possible.
Okay, and I have to look how it works. Yeah, here. Maybe this one. And now I have to look for the right window from the application. Which is, yes, it has to be this one. I hope so. Yeah, okay. So, can you see it? Can you see the picture?
Yes.
So, our application is not a flexible shaft. We have the problem that the running belts, they are driven with the gear, and the running belts from this treadmill are going from the upper side to the downside, and they are moved via this chain, and the treadmill is going in all directions. So when it's coming back, then the thing is that this teeth here, I hope you see my mouse also. The driving teeth should fit back into the envelope of the gear from the shaft, and this was the reason that while rotating the running belts around here, they are not allowed to move anything in axial direction, because then the wheel doesn't fit back. So of course we did a little bit of phases here inside, but we have to avoid that these clashes to the front of the shaft. Bearings, we have ball bearings here inside the belts, but this is not the thing of the transferring the moment or transferring the torque while the rotation. The torque is only transferred here via the normal envelope gearing. But the necessity was to find back the way into the gearing. So maybe it's not too similar to your application, or I'm understanding it right or no?
Yes, thank you for your answer. It's much clearer to me now. Thank you.
Yeah. Okay.
Manfred, just to follow up on that, were you able to maintain the constant velocity ratios that you were looking for as you varied the angle?
The velocity from the treadmill.
Yeah,
you mean?
between across the gear mesh, in your experimental setup. Was there any indexing action in the
In the experimental setup, we changed also the rotating direction. We changed the driving angle, and we changed also rotating direction for moving back and forward.
And you found a very smooth.
Yes, because it was necessary that we have no flank distance or no movable possibility between the
right,
directions.
No backlash. Yeah.
No. Yes. No backlash, and yes, this was useful. So the gearing system that we found out is usable for this application.
Okay, that's excellent. Very, very innovative, and I like the approach, of course, of verifying it through a test.
Okay, thank you.
Now, Daniel, we didn't ask you a question yet, so part of my job as a moderator is to make sure everyone has a chance to talk about their contribution. I think you mentioned in your presentation the issue of lateral and torsional buckling, and I think I remember from a course a long time ago that this can be mitigated by the use of plates that are welded between the flanges. I'm not sure if they're called intercostals, but I think you know what I mean. So how could those be incorporated in your model, or have you thought of incorporating something like that?
This was initial research. So in the future, we will attempt to include more details. As you said, plates that will increase the stiffness of the web. And also we wanted to include the holes into the web to remove the unnecessary masses.
Right.
Mass on the middle of the web will not add to the bending resistance. So it could be incorporated. We would just have to include more parts into the equations, and also additional weldments that will be required.
Good. That might really be useful, because there's a bit of a trade-off between the amount of material you use and the labor content you're putting into the fabricated structure, I guess.
Yes, in some cases it can be cheaper probably to just not alter the vertical web. So because the cutting cost could be greater than the material costs.
Right.
And also the plates from the middle, the cutouts could not be probably used. Depends on the application.
Yeah, good point. Yeah. Okay, we still have about 5 minutes left. Are there any other questions from our participants? I haven't seen a question from our non-panel participants. Okay, in the meantime, Aljoscha, I know you mentioned that you were intending to move forward to test your design for noise and vibration. What did you incorporate from a design point of view to sort of address noise and vibration? Because this is an important parameter to consider in the design of this engine.
Yes, Oscar, it's a very important aspect for the mobile application, for example, as range extender. Currently, for the crankcase, we neglected the effects. So ideally, we would have avoided great plane areas that can transmit noises. In the future, we want to complete our design process for all parts: cylinder head, cylinder block, and crankcase. And want to include simulations to get responses for the vibrations. We can already measure it at our test bed, but currently we have no way to simulate it. So that's a tool we have to integrate in the process.
Okay. We talked a little bit about this when we met before the conference. You used quite a number of separate tools in your design, as you showed in your process flow. And did you find that the digital transfer of information was effective enough for your work, or could it be improved?
It worked for our design goal, I would say. It's a bit cumbersome because we had to switch between CAD systems, CAX systems with finite element analysis and so on. But that's also due to our software that's available to us. Industrial clients have their own systems where everything is integrated, like CAD and FEM. But we have a lot of separate tools, so we have many breaches between the systems where we have to exchange data. Yeah, overall, a complete simulation suite would be nice.
Yes. Yeah. Okay, good. Good. Yeah, I really enjoyed that design. Okay, we have a question from Ryan Rivald. I know Ryan, to Marius. I don't know if you can activate your microphone, Ryan. If Ivan, can we do that?
No, he has to ask to share his audio. Oh, yes, he asked.
Okay. Can you give him permission, please? How you doing, Ryan?
Yeah.
Go ahead.
Quite good. How are you guys doing? I think I'm looking at the wrong camera on my desk, but
That's okay.
I'll solve that one way or another. Yeah, I'm just curious because I also work in the early, quote unquote, early phases. And I get that as a question quite often, how are you defining what is early? Is it before any requirements are made, or is it after some requirements are made? I mean, how much freedom do you have in whatever these quote unquote early phases are? So I'm just curious in your mind, when you're coming to materials, how are you defining the what phases you mean?
Yeah, definitely a good question. Where do you set the boundaries? I think some of our work goes into that. A lot of the requirements are actually created and derived during the early phase. So it's sort of using, in at least our use cases often is using prototypes to elicit and sort of establish these requirements. So I would say the early phases are before you sort of set a concept to be refined or developed. In a product development context, I would say end of the fuzzy front end, where you decide to invest more time and engineering resources into bringing a concept towards market or the next steps. Would sort of be the boundaries of where I see the early phases of design. It's also where you should probably invest time and resources in order to make sure that you don't follow a dead end, which can become costly later. The reason why I won't say that non-rigid materials are either more or less applicable. I just think that sort of the recent advances in a lot of research in this field, both in medical technology, you have soft robotics, compliant mechanisms. All of these are heavily reliant now on prototyping in order to sort of do them in a research perspective, but also when we look at using them in conceptual prototypes. I think they should be included, even though there might be a lack of how-to instructions. So that's why I think they are well-suited prototyping, and also keeping in mind when we do our stage development, because a lot of concepts are revolving around 3D printing and laser cutting, and that mostly concerns rigid materials. So I thought, especially in our sort of field, where I work a lot with emulating the human body for medical training, we are solely reliant on having flexible components in our prototypes. So
good.
So you think it's, sorry, can I follow up or
Yeah,
are we
just
out of
very
time?
quickly. I want to keep us on time. Yeah.
Sorry. Yeah, I'm just going now. Now I lost track. All right, I'll write to him. I'll write to him later. It's fine.
Yeah. Thanks, Ryan. Thanks for
Marius.
that.
Thanks.
Okay,
Appreciate
so we have one more minute left. Thanks very much for that question, Ryan. I just want to take this last minute before our refreshment break to thank very much all of our speakers and our contributors, Manfred, Daniel, Shayne, Tim, Aljoscha, and Marius, for really good work. When you go to practice and you produce something, it is easier said than done, as they say, right? So thank you very much for your contributions. Also, thank you to Ivan for smooth technology. The video problem is on my side, I'm pretty sure, so I apologize for that. Next is our refreshment break, and then a second keynote. But I hope to see you all in the Gather Town, the social event, and hopefully my video will be working then. And I look forward to seeing you all at the conference. Thank you very much, everyone.
Thank you.
Bye.
Bye.
Thank you.
Thank you.